Today's discussion will offer a novel and unified perspective on both life and intelligence, as described in Blaise's new book, What is Intelligence? Lessons about AI, evolution, computing, and minds. We will start by a presentation with a presentation by Blaise and a follow-up Q&A session moderated by Ricardo. Welcome, everyone.
Thank you for the really kind introduction, and thank you, Ricardo, for having me here. And thank you all for coming. I think it is maybe a little bit, yeah? Okay, so the book, What is Intelligence, just, the publication date officially was yesterday, so it's now out. It's also online for free at wii.antikythera.org, with actually a lot of rich media that are not possible to put into a print book. So, my hope is that that some of the things that I'm writing about will get a wide readership. I guess we should try to buy books in order to keep MIT Press going, but it's definitely not the way I'm making my living, which, thank goodness, given how little the book writing business seems to pay. Anyway, I should say a little bit about my history very briefly. So in my previous role at Google, I spent almost 10 years running a part of Google Research that built most of the AI features that go into Android and Pixel phones. And this is something that I always thought of as building narrow AI models. So things like face recognition for unlocking the phone, or music recognition for recognizing what's the ambient song playing right now, often using local models. So a lot of this was very privacy minded. We developed techniques for doing decentralized learning so that you could learn models without actually sharing private data in a kind of decentralized way. And one of the models for which we used federated learning was the next word predictor of the Google keyboard, which some of you probably have used. And there are similar ones on the iPhone. For those of us who never learned how to type properly with our thumbs and are like pecking around like old people with a forefinger, this can speed up typing. And it's just a statistical model that builds up statistics about word sequences and then predicts the likely next words. I of course did not assume that this could actually produce a truly intelligent system. It's as I've said a couple of times, like it would be easy enough to predict Dumpty after Humpty through statistics, but if the next word is the answer to a word problem, or how somebody feels, in the middle of a narrative, describing some personal interaction, then giving the right next word would imply understanding what's going on, or being able to actually do math and so on. So the idea that a next word predictor could solve those kinds of problems just seemed impossible to me. And I assumed that the answer would come from neuroscience, and that then we would apply some of those insights to next generation neural nets. This is the core AGI hypothesis as framed by Ben Goertzel in 2014. Synthetic intelligences with sufficiently broad, e.g. human level scope, are qualitatively different from synthetic intelligences with narrower scope, meaning AGI, artificial general intelligence, and artificial narrow intelligence are fundamentally different things. Artificial general intelligence, so this distinction was coined around the year 2000, and AGI is just what we meant by AI back in the old days when we were growing up, as opposed to when we began using the term AI as marketing hype for narrow features like face recognition. Now, it wasn't just marketing hype, to be sure. Like, we were starting to use neural nets to do those things, and tasks like object recognition, face recognition, speech recognition had been recalcitrant to being to solutions using ordinary engineered code, and so and neural nets were actually brain inspired. So there was some hope that we were moving in sort of a useful direction for working on brains, but general intelligence seemed like a whole different sort of thing. It turned out that intuition was wrong. And I began to really feel that way when I started to see very scaled up next word predictors or next token predictors. The first one was Mina, which was developed, I think, in 2019 originally. And you know, it's just predicting next words, but as it predicts next words in a conversation, you can have a conversation, you know, you can have a talk with it about philosophy. And here it is, you know, attempting to define philosophy in a conversation. So this began to really make me think twice about this distinction between artificial general and artificial narrow intelligence, because it's just a scaled up version of what we had been making all along with the next word predictor on the keyboard. Lambda was scaled up even further in 2021, and it could have even more sophisticated conversations. And so at this point, I began to wonder whether, in fact, our brains are also just next token predictors. I know that that's still a very controversial statement, the idea that we are just statistical predictors of the next stimuli given the past sounds maybe a little bit dismissive about humans or about intelligence or about what it is. But I think that we need to take this possibility seriously and ask ourselves what it might mean if that were the case. I should say that continuing to scale these models up further has continued to make them smarter over the past 5 years. So, you know, because everybody realized that, you know, that this scaling made systems better and better, there's been this, you know, there was already a kind of exponential scaling and parameter count of bigger and bigger neural nets starting in 1950 when you know, some of the first neural nets were made. But this has really accelerated since 2015 and especially since 2020. All of this suggests that the core AGI hypothesis is wrong. Okay, so could we be just massively computationally scaled up predictors too? Is kind of the question. And I'm going to, you know, boldly or foolishly suggest that maybe the answer is yes. And that's really the premise of the book. That raises a whole lot of questions, including why would a brain evolve to be computational in the first place? Why would the thing that it evolves to compute be a prediction of what comes next given the past? Why has its computational power grown explosively? Because, you know, it's not just Moore's law that has been growing explosively since 1950 or 1970 or what have you. It's also brains, right? We also, you know, if we have these giant complex brains in our skulls, if we go back by 100 million years, nothing with anything like that big a brain existed. Go back another few 100 million years, nothing with any brain at all existed. Just diffuse neural nets a few 100 million years earlier, and no neural nets at all. So, you know, how can we explain that growth in computational complexity on Earth? And what happens now that we have AI? Now, there's another big question here that I don't think I'm going to be able to talk about, but maybe we'll get to it a little bit in the discussion, which is, why does it feel like anything to be a next token predictor? That's a big one. Okay, so why would a brain evolve to be computational? Well, after thinking about this for a while and doing a lot of research, I started to realize that it's life itself that has evolved to be computational. And this is kind of the theme of chapter 1 of the What is Intelligence book, which is we've also kind of published on its own as a sort of single. You know, it's like a record where like the single gets sold to a little book called What is Life. So this little What is Life book actually kind of fits into What is Intelligence as it's chapter 1. Some of you might recognize that name is ripped off from Schrödinger in 1944, who also wrote a book called What is Life. And in fact, there's a whole book about all of the books that have been called What is Life that has also been published, but never mind. Okay, so living systems. Back in the 19th century, there was the idea that what makes life alive is that we have some kind of animating spirit, some élan vital that, you know, that makes us go. And that idea, of course, fell out of fashion in the 19th century as we began to realize that the rules of physics and the laws of chemistry that govern the matter in our bodies and the chemicals in our bodies are the same as the laws of physics and chemistry everywhere else. There's nothing special about the matter in our bodies, and the matter in our bodies is no different from any other. And so this led to, you know, this kind of radical materialism, which is where I would say most science still is. But I find that quite unsatisfying too, because you know, then like what is different between us and a rock anyway? You know, like it seems like there's something different. It's not, if it's not different in the physics and the chemistry, then what in fact is it? I think that there is an answer, and that answer is function. So functionalism is not about the rules that govern the physics and chemistry, but about what it's for. And this is also a perspective that that kind of smells a little bit of teleology, which biologists are very afraid of. But I want to lean into it because I don't think that there's any way of talking about biology without talking about function. So, for instance, if we talk about what a kidney is, you have to talk about what it does. It's about filtering the urea from blood, and that's not something that the atoms tell you. It's something that is about how it functions or how it works in the context of the rest of the body. So if, for instance, I am a time traveler and I come back from the future with this object, and it's made out of shiny metal and it's got carbon nanotubes on the inside and so on, and you ask me like, what is that thing? And I tell you it's an artificial kidney. It has a 100-year lifespan. You can implant it into the body and it'll do the same job as a kidney. I've just given you real meaningful information, but it's not like those atoms say that, right? That information is not in some way imminent in those atoms. It's really about the functional relationship that this would have if implanted in your body with the rest of your body. And so that's very real, but it's also not material in some fundamental way, in the sense that there are many different instances, many instantiations of such a system that would serve that function. Maybe it's carbon nanotubes, maybe it could be done with tungsten filaments, maybe it could be done with synthetically grown blood vessels, who knows, right? It's the function that matters, not the implementation. This idea of function is one that really was articulated and theorized by Alan Turing. And Turing, for me, connects the idea of function that we've been talking about with the mathematical concept of function in the Turing machine. Right, so I'm sure all of you know more or less what a Turing machine is, but it's an abstract thing. Here it was actually physically built by Mike Davey, although it was never meant to be built. But it's a tape and a head that can move left and right along that tape, reading, writing, and erasing symbols according to rules on a table. And Turing's big innovation was to say, well, you could, given an appropriate table of rules, actually take a second table of rules and encode it as symbols on the tape. And with an appropriate table of rules, it will read the second table on the tape and run that calculation that is written on the table. And that would be a universal Turing machine, meaning a Turing machine that can not just calculate one thing, but can calculate anything, because you can write any rule table that you want on the tape. That's, of course, what a computer is. Now, there's a second big thinker who I think added something really important to Turing's idea. This is John von Neumann, also one of the founders of computer science, also a mathematician by training. And von Neumann was thinking about the problem of life. He should have written a book called What is Life as well, because I think he came up with one of the most powerful answers around 1950, maybe a little before. The puzzle that he was trying to solve was, how is it that if you're, let's say, a robot made out of Legos, and you're paddling around on a pond with lots of loose Legos floating around in it, how can you assemble those Legos into another robot like yourself? Which seems almost like lifting yourself up by your own bootstraps, right? It seems like there's like a whiff of impossibility or paradox about that. But that's, of course, what every life form has to do. That's what a bacterium has to do in order to divide. It's what a mother has to do in order to give birth. And even if you don't reproduce, it's what you have to do in order to be autopoietic, which is Varela and Maturana's term for the thing that all life has at its core, which is the ability to self-construct. If you're an octopus and you lose an arm, you construct a new arm, which is an octopus arm and not a human arm. That's autopoiesis. Anytime you heal, grow, or reproduce, you're doing autopoiesis. You're constructing yourself. So von Neumann's answer to his own question was, well, in order to do autopoiesis, a term that had not been invented yet in 1950, but never mind, you have to have a tape inside yourself that describes the instructions for how to build a U. And you have to have a machine that will move along on that tape and carry out the assembly instructions. And you also have to have a tape copying machine, so that if you have offspring, you can make a copy of that tape for the offspring. And by the way, the instructions for the universal constructor, which is what he called that machine that would move along and build, and for the tape copier have to both be written on the tape as well. So as long as all of those conditions hold, you have heritable reproduction. And what's really cool about this, about von Neumann's insight, is that he had it before anybody had characterized the structure and function of DNA, or knew what a ribosome was, or had observed or characterized DNA polymerase, which is exactly the tape copying machine. So he called it correctly. That's exactly how biology works. But the really cool thing is that he also realized that this universal constructor is a universal Turing machine. They're the same thing. And that tells you that life is inherently computational. If you can't compute, you can't do autopoiesis. Doing autopoiesis is literally computing. That's what life is. It's computation. And in particular, it's an embodied form of computation. This is really important because it's a little bit different from Turing's version of computation, in the sense that in Turing's version, the only thing the machine can do is read and write symbols on the tape. It can never print out a new tape head or a new tape. Whereas in von Neumann's version of computation, the symbols are actually the same stuff that the computer itself is made out of. These are cellular automata. And so what that means is that not only can it write abstract symbols, it can write another computer. So you should think of it not just like a laptop, but almost like a combination or a mashup of a laptop and a 3D printer. Right? A von Neumann universal constructor is something that whose memory is atoms, not just bits in the abstract, and that can print out another one of itself. Okay, so you can't reproduce without computation. No computation, no life. Life is computation. That's what it is. So this is why artificial life is a field. Artificial life is trying to get life-like processes to happen in computational environments on a computer, just like artificial intelligence is getting intelligence to happen on a computational environment. But the reason that one can do meaningful experiments in evolution and in life on a computer is because this thing is inherently computational in the first place. So this is an experiment that that I began playing with in November of 2023, and we published with the team in last summer in June of 2024, and it involved getting something to happen that I don't think has quite been done before, which is to get self-replication or get something lifelike to happen in an artificial life system from nothing, starting with just random noise. This is the problem of abiogenesis. How does life start from nothing? Which really puzzled Darwin. Like Darwin, found this like the hard problem of his time. Lord Kelvin thought, that evolution definitely works, but it only works once you already have life. So God must have created life, and then everything after it happened, according to Darwin. But this is the disproof of that. Here's how it works. So we start with a very, very simple Turing complete language called brainfuck. And I chose this language not only because it's really fun to give formal talks in which I say brainfuck a bunch of times, and I'm fundamentally 12 years old, but also because this language, not named by me, by the way, this is invented by Urban Miller, a Swiss physics grad student and amateur juggler in the 90s. So it's a really minimal language that has only 8 instructions, and it's modeled very closely on a Turing machine. So the first 4 of those 8 instructions are move the head 1 step to the left, move the head 1 step to the right, increment the byte at the head by 1, decrement the byte by 1, and that's already half the instructions. The other half are for looping and for input and output. Very, very simple, but it's Turing complete. You could write Windows 95 in this or whatever you want with enough patience. Okay, so the setup for this artificial life experiment is that you start off with 1,000 tapes of length 64. And the tapes are filled with random bytes. Remember, there are 256 possible bytes, and there are only 8 instructions in the brainfuck language. So only 1 in 32 of those bytes actually codes for an instruction, and all the rest of those byte values are no-ops, meaning that if they're executed, nothing will happen. The instruction pointer will just continue. The head will just continue along. So this is what the tapes look like in the beginning. They're random. I'm only showing you the values where there are instructions. And the procedure is very simple. You just take 2 of these tapes at random, You stick them end to end, you concatenate them, and you run, and then you pull them back apart and you put them back in the soup, and you repeat millions of times. That's the whole experiment. In the beginning, nothing much happens, because there are very few instructions on these tapes. The instructions don't do anything interesting. Once in a while, it'll modify a byte somewhere else. Seems not very promising, right? So let me show you now what happens. Luckily, it's a really simple language, so it can run really fast on a laptop. And after a few million interactions, something really cool starts to happen. You see structure, and then you see complex programs emerge in the soup. And this is really cool because these programs are not right. They're not inoculated. Nobody wrote them. They just emerge from pure interaction between random instructions on these tapes. And so the question, what are they doing? I guess you can answer by just noticing that there are a whole bunch of copies of all of those different programs on the resulting tapes. It'll be different programs every time, but in every case, they're copying themselves, copying each other. So copying themselves is what they end up doing. Why is that something that happens? Well, clearly, if something copies itself, it will still exist in the future. If something can't copy itself, then it will get overwritten by something that can. So, what that tells you is that there is a kind of, it's favored to find something that can copy itself because those are the things that will persist through time. In other words, there's a kind of Darwinian selection for things that can reproduce that begins even before life exists in the first place. So that's really interesting. But and one of the side effects of this is that there's a dramatic rise in computation. So in the beginning, there will be 2 operations that run on average in every interaction. But after 5 million interactions, you get these complicated programs, and more than 1,000 operations are running per interaction. So it's suddenly become very computationally intensive. This is what that looks like. So I'm drawing here 10 million dots on the x-axis, which is time. 1 dot for every interaction, and the height of the dot is how much computation took place in that interaction. And you can see that there's a phase transition right at 6 million in this case, where it goes from not much happening to suddenly like a wall of computation going on. That's the emergence of life. Okay, so the hypothesis that emerges from this simulation and others like it is that in pretty much any universe that has a source of randomness and that can support computation, life is going to arise because it's favored, because it's more stable in a certain sense than non-life. Not stable in the usual static sense, but stable in a dynamic sense, in that it creates more of itself. There's an old joke about DNA being the stablest molecule in the universe, right? Not because it's particularly robust. It's actually very fragile. But leave 1 DNA in the beaker with DNA polymerase, and you get a zillion DNA the following day, and that's more robust than granite, which can only go downhill over time. So there's a puzzle here, though. There's a conundrum, which is how on earth do you get these very complex programs in only 5 million interactions, starting with only 1,000 tapes of length 64 with random bytes in them? The usual story about evolution is that it's all about like 1 million monkeys on 1 million typewriters, or spaghetti throwing at the wall and see what sticks. And it would take a lot more spaghetti and a lot more wall, or a lot more monkeys and a lot more typewriters than this to get really complex programs like that. So there's a conundrum here about how the evolution could result, how ordinary evolution could result in these very complex programs. And as I began to explore what was going on, I realized that Lynn Margulis had the answer. So she was the one who figured out in the 1960s that eukaryotic cells are made from the endosymbiosis of a bacterium into another prokaryotic cell to create mitochondria and the containing cell, eukaryotes. This was so this is symbiogenesis. And she believed that symbiogenesis was the driving force behind evolution. But even by the time she died in 2011, that was definitely not mainstream biology. So she convinced biologists with difficulty that this is how mitochondria had arisen, and chloroplasts and a few other things. But the idea that symbiogenesis, that things coming together to form new complex things, was a big driver of biology, still very much not mainstream biology by 2011. It still isn't. But that's exactly what's happening in this artificial life system that I've just shown you. And in particular, the way you can see that is by looking at smaller strings, at smaller sequences of bytes that end up getting copied. And if you look for strings that get copied, you find that there are 1-byte sequences that get copied now and then, even at the very beginning. They're weak replicators, they're not great, but basically, given that there are some instructions that will change a byte somewhere else, right? One of those instructions in the right spot and under the right circumstances will change another byte into another instruction. And that's a form of very, very weak replication. So once in a while, you get instructions making other instructions. And once in a while, those copies will end up in conjunction in such a way that what gets copied is longer than one instruction. It's 2 or 3 instructions. And it turns out that basically that cascade of things combining into bigger things is exactly the process that results in these big complex programs. It's a symbiogenetic process. And that's the creative process that leads to these big and complex things. That's really interesting because it actually gives evolution an arrow of time in a way that it doesn't have if you just think about standard mutation and selection. Ordinary mutation and selection is zero-sum. It just involves things competing with each other to see which one is going to win. And there's no rule that says the winner should be any more complex than the loser. It may be simpler, it may be more complex, but there's no arrow of time there. Whereas in symbiogenesis, there is an arrow of time because if 2 things combine to make something that also replicates, then the combined thing is generally more complex than the things that combined, right? It has to know how to make part A and part B and how to put parts A and B together. So if you do that repeatedly, then all of those merge rules basically are the complexity of what you end up with. Now, in 1995, Yor Sathmari and John Maynard Smith, systems biologists and evolutionary biologists, wrote a famous paper called The Major Evolutionary Transitions, in which they noted that symbiogenesis, as Margulis had described, has taken place on Earth at least 8 times with major effects. This included not only the eukaryotic transition, but also things like the aggregation of humans into societies, which is obviously a major symbiogenesis, or the aggregation of single cells into multicellular organisms like us, or the aggregation of solitary insects into hive insects, as happened with wasps and bees and a few others, and ants, I think, a couple of 100 million years ago. So originally they had like 8 of these. They added after that maybe another 4 that are also big deals. And basically what I'm saying is that even Smith and Sathmari are not going far enough. They're talking only about some of the biggest, most consequential symbiogeneses, but they're happening all the time. And to notice that they're happening all the time, all you've got to do is look inside our own genomes. So this is the human genome as it was sequenced by Lander and co. In 2001. And the first thing that a lot of people noticed about it is that only 1.5% of it even codes for the proteins that make up our bodies. The rest of it is all this so-called junk DNA. Now, it's not really junk. A bunch of it is involved in protein regulation. But what's really interesting about this breakdown is that those LTR retrotransposons, DNA transposons, lines and signs, and probably some of the other parts as well, are all viral sequences that basically replicate themselves inside genomes and across genomes in many cases too. 1/4 of the cow genome is the BOV-B retrotransposon, which is also horizontally transferred to salamanders and a whole bunch of other bizarre animals. That doesn't look like the kind of evolution that we all grew up with, where it's just random mutation and selection. It looks like it's a sort of frothing chaos of replicators of all different sizes. You have like robots made of robots, made of robots, made of robots, all of which are replicating themselves. And it's a really different picture. And by the way, we also know that a bunch of these viral endogenization events have resulted in functionally critical things in our bodies. I think probably all of the functionally critical things in our bodies, but among the ones we know of, are, for instance, the ARC virus, which is what somehow allows us to form memories. We know that if we knock it out in the mouse, then they can't form new memories. There is another virus that resulted in the fusion of cells to form the plasma in all mammals. Sorry, to form the placenta. So placental mammals, that's all viral endogenization as well. A lot of this research is just last 10 years, and more and more of these things are coming out. And of course, the longer this viral code that has been incorporated into our genome stays there, the more it kind of gets filed down and becomes less and less recognizable as having originally viral origins. So, an easy guess is that this is the engine behind the creativity of evolution in general. It's not just neuroscience that's computational. Life was computational from the start, as von Neumann realized. It gets more computationally complex over time through symbiogenesis at many scales, right? I mean, remember that since life is computational from the start, every time there's a symbiogenetic event, you now have increasing parallelism of the computation, right? You now have two computers that are replicating themselves and need to interact or model each other in order to effectively work as a group. And cascades of that mean that there is a kind of Moore's law at work here of parallelism, of parallel computation. That's in a way the theme behind the book. And it does give evolution an arrow of time, and that arrow of time is a computational arrow of time. Symbiogenesis makes this computation massively parallel. Computing for growth, healing, and replication is modeling your own body. That's life. And when you model your environment, and that's also needed when your environment is dynamic, especially when your environment consists of others, that's what intelligence is. I mentioned in our earlier conversation that not only was life intelligent from the start, but that all of the intelligence explosions that have resulted in complex animals with big brains like us are the result of social interactions. So we've seen, and I'm gonna skip just to this plot, and we'll end here, and then we'll go into discussion. But this is our own intelligence explosion among the hominins. So we started as anthropoid apes, and then there's Australopithecus and Homo habilis, and so on. In these 7 million or so years, our brains grew much bigger, and the reason they grew much bigger is because we needed to model each other in social groups. And as you're able to better model others, you gain a certain advantage in competing for mates, in being able to do politics, and so on. But also you gain a group advantage because you're collectively with your colleagues able to divide labor better and do all of the various things that the Growth Lab studies as essentially the origins of economic growth. And so there's an individual level advantage, a group level advantage, and the collective intelligence of the whole rises, and it forms a feedback loop, right? If you're trying to model others, and you grow a bigger brain to model them, well, they get a bigger brain too because you share genes. They become harder to model. Now you have to get an even bigger brain, and so on. That's this exponential explosion. Okay, and this is just troop size versus brain size, or size of neocortex relative to the rest of the brain. This is Dunbar's results, which I'm sure many of you are familiar with. Basically, I'm saying Dunbar's law, or this social brain hypothesis, goes all the way down to single molecules. And it's actually the story of all of life, not just the story of monkeys and brain sizes. And with that, we should probably switch to discussion mode.
I mean, this is incredibly insightful that you can get, there's a natural selection of things towards complexity. And at the core of it is the ability to replicate. And if you want to replicate at a higher level, then you have to simulate the other in order to interact with the other in order to replicate. And then you have this explosion of things. Now, you're thinking about these things because you're at Google.
Maybe.
Or there's some interaction between that.
Yeah, for sure.
So why do you see that thinking about these fundamentals is important for your day job?
Well, I mean, luckily Google is humoring me and continuing to pay my salary and pay the groups, despite the fact that we very explicitly set out 2 years ago to not make products, but to work on fundamental things. Partly I think that that's because we kind of paid our dues and we did a lot of stuff that was useful for the company in the previous decade. But also I think my boss James Manika and I had a lot of conversations about the way in the past few years as the race has gotten really there was the firing pistol fired and a race began between OpenAI and Anthropic and Google and China perhaps and so on. There was a real need to make sure that we were actively investing in basic research as well, and the things that gave us transformer models and AI in the first place. And so with this big turn toward product, we needed to make sure that we were also doing this.
So if you were to think about the interaction between this basic research and where you think, so how is this research in some sense synthesis? I mean, you want to do artificial intelligence, it sounds like, why don't you start by asking a question, what is intelligence, right? Which is what you're doing. And then how does it grow? Because we are seeing the growth of LLMs also. So what are the parallels between this general understanding of intelligence and what's going on with artificial intelligence?
Well, I mean, as I see it, so first of all, yes, I mean, all of the work on scaling laws in AI models, if you understand this in terms of parallelism and the natural division of labor that happens inside models, for instance, or in cases of mixtures of experts that are imposed on the architecture of all these things, then it's all instances of the same thing. We're looking at the same phenomenon, and understanding the natural science of that phenomenon should have practical, it should help us, right, in the engineering too. In the same way that, understanding the laws of thermodynamics, if you're making engines in the 19th century, will certainly help, right? It'll help you to make better engines. I feel like we're in a time now where the practice is ahead of the theory, in the same way that in the 19th century, practice at making heat engines was ahead of theory until Boltzmann figured out thermodynamics. For much of the 20th century, I think things were the other way around. Our theory was ahead of our practice. We had a lot of science fiction. We knew, in principle, how to get to the moon and so on long before we did it. But now, we're back in 19th century mode.
That's super insightful because there's always been this coevolution of, call it science and technology, for lack of a better term. But and you think, I mean, the standard model, you'd think that technology comes after science, but
not always.
But the truth is that there's been very strong interactions between the two.
Right. And by the way, that's happened. I mean, so the local version of that is computational neuroscience to neuro AI. So, computational neuroscience, is sort of, studying brains as computational systems. And all of the innovations in AI came from computational neuroscientists up until the transformer, until 2017. Softmax and rectified linear nonlinearities and convolutions and reinforcement learning, and the list goes on and on. But starting around 2017, the shoe went on the other foot. And so now, many people in the field, when they get together, neuroscientists and AI researchers together, they now start calling it neuro AI. So they've flipped the ordering of the names. And I was in a panel a couple of years ago at COSIGN at the conference, a big computational neuroscience conference, and I was the one singing the praises of neuroscience at this conference, while Tony Zader, neuroscientist, was being very gloomy about, is there any point anymore in studying brains, because now the engineers are ahead, and I think on the contrary, like there's a huge point, but we now have to our theory has to now catch up, rather than always just being the guide.
Maybe we can start opening up for questions.
Well, yeah, it's a good question. So, I mean, there's a really deep question about the relationship between a physical system, a dynamical system in general, and computation. Actually, I met somebody here. What's his name? Joshua Jordan. Shit. What's his last name though? Okay. He's working in the quantum computing lab, but has been doing a bunch of work on A-Life more recently. And he has some very nice insights about this. But basically, if you have a dynamical system and you want to map it to a computation, you have to coarse grain it in some way. So in a computer, for instance, your coarse graining says like which voltage values are a 0 and which ones are a 1. And then you can talk about an abstract evolution of a state space computationally. And then there's a physical evolution of the state space of all the atoms in the computer, and you can make a mapping. And the way you confirm that it's a computer is by saying, the evolution of the physical system and the evolution of the computational system continue to match each other. You also have to add in a constraint that your mapping cannot be so complex that that just like the movement of a river qualifies because you put all the complexity in the mapping. So that's how you make that analogy. Now, there isn't necessarily an a priori reason to say that any dynamical system isn't doing some computation, but there's also nothing to favor one coarse graining over another until you get the emergence of function. So, once you start talking about function and selection for function, now there is a coarse graining implied in what the thing is actually doing. You still have to have a model of the model. So there's something self-referential about this whole thing. But again, you can use an Occam's razor type argument to say when what you're describing is real. I hope that makes sense.
Yes, so what is Google actually looking for to get out of your research? Because, so what are the next big steps a giant company as Google would like to, to get knowledge about an AI?
Well, I mean, I think part of it is just, do the science, and learn more about what we're doing. I think it's always good to understand the fundamental principles behind what you're working on, and that generally results in improvements to it. I mean, I could give a few practical examples, like, for instance, these mixture of experts type models and how they scale. If we're able to relate that to, to essentially connect scaling laws of models with social science, that could suggest new social architectures for AI that are more efficient, that scale better. One could imagine ways of doing AI in a more energetically efficient way by using some of the more A-Life inspired techniques that we've been playing with. But I think the science, it's worthwhile to invest in the science, even if you don't know exactly where the practical benefits.
It would be interesting in any case to share, because the audience may not necessarily know what were if you were to describe what happened to AI in the language of your interpretation of life or of intelligence that you've just explained. So you've explained the bare bones of what intelligence is. And if you applied that understanding to kind of the evolution of AI up to now and what you see going forward, how would you?
Yes. Well, so I guess what I would say first is that there were two wrong ideas about what intelligence is that predated the current sort of explosion and success of LLMs and things like that. The first was that intelligence was highly rational and could be formulated in terms of expert systems, rules, grammars, Chomsky kind of stuff. And this led to the AI winters, the sort of lack of progress throughout the entire 20th century. Minsky was, an advocate of this. And there's still a few advocates, around of like symbolic systems and stuff. None of it worked. None of it can even do simple things like recognizing objects or whatever. And this goes all the way back to Leibniz. Leibniz originally, imagined that intelligence could be reduced to a formal language, and that you would be able to write down propositions and compute whether one thing or another is correct. Not just what's the value of pi, but like, should same-sex marriage be allowed, or something. And and I think we now know that's not a thing that can be computed by axioms. The second wrong idea is that AI is just an optimization process. And this one came from, after we began to do machine learning and train models, but and the power of gradient descent became clear. We began to see that that maximizing some value was a way to train a model to to do better and better at something. And when we were doing narrow AI training, then we could define that better and better in simple terms, like better and better face recognition, or better or lower and lower error rate on word transcription, or what have you. And this idea that intelligence is all about optimization fits very well with neoliberal economics. It also fits very well with utilitarianism and the effective altruists and the rationalists and all these guys. It's actually a very scary idea of what intelligence is, because there's almost nothing that you could imagine, a super intelligence maximizing or optimizing that isn't bad, like that doesn't lead you to a paperclip monster type scenario. So none of that actually, we didn't find a magic thing to optimize that led to general intelligence. What we eventually did was to do unsupervised learning. It still uses gradient descent, but what it's trying to do is just model, all of the human activity that we've put on the internet. And it's certainly not optimizing anything, in the sense that when you're chit-chatting with with Gemini or something, there's not some problem that it's trying to solve. Necessarily. You can set it a task, but the whole point is that it's general, it's open-ended, right? It's not maximizing anything in particular in that interaction. So that general modeling or general prediction, turns out to be the key.
And why has it gotten so much better?
Size. When we there have been two epochs of scaling in computation. The first one lasted from 1945 until 2006. And during that era, we had Moore's law and Kumi scaling, meaning that not only did the transistors get smaller and smaller, so you could fit more and more of them on a die, but but also the clock speed increased until we were getting into the gigahertz. And so programs ran faster and faster, and computers were smaller and smaller and cheaper, and ran at lower and lower power. But notice that AI made no progress during that period, because a giant grammar or expert system, is not any smarter just because you can run it faster. It only began working when we began parallelizing, which started happening in 2006, which is after Kumi scaling ran out, and we stopped being able to increase the speed the processors and instead began to parallelize them and put many cores on the same chip. At that point, originally games were the customer, so pixel shaders and video games, but AI researchers latched onto that because neural nets are also highly parallel, and that's when we began to see progress in AI. So I think really 2006 was the watershed.
Yes.
Hello. Thank you for the talk. I had a quick question based on your experience on the access to this intelligence. So I sometimes think about, let's say, the travel industry. We've developed the most sophisticated, best travel systems, but people do not get access to it because the unit economics works differently across different customers or the businesses. Now, as we're thinking about this access to AI labs, I've recently seen the free access has been going away. The price of the models have been going up, like deep research and those things have been now limited. So do you feel like going forward, how can how can this access to this intelligence stay universal or kind of kept universal? Or do you think there is still going to be inequality in this scenario?
Well, I don't know. I mean, I'm hopeful that we're going to end up with abundance in AI. We certainly have tremendous abundance relative to what we had a year ago, and a year ago it was abundant relative to what it was a year before. Our kind of demands and our expectations have gone up faster than the supply of chips. You know, that's really what it boils down to. But you know, I think that for instance, the fact that TPUs are not broadly available and NVIDIA is limited in the rate at which it can make chips and has been charging an arm and a leg for them as well, I don't think it's sustainable. You know, I also don't think that those architectures are the right ones ultimately. You know, they're still based on ordinary serial computing of the same kind that we've been doing for 70 years. And my guess is that efficient neural computing, where the transistors on the chip have a much more direct mapping to virtual neurons, right? We're not kind of just running programs. I suspect will increase the efficiency tremendously and decrease the costs. I also think that we forget that the open source models that you can run on your laptop or even on a phone are only half a year or 9 months behind the frontier models. And those are not only abundant, anybody, even many people in developing countries on their phones, right, can run models like that in principle today. So I see the gap between the leading edge and the ubiquitous being pretty thin and shrinking. I hope I'm right about this.
Thank you for your time today. So I guess many of the governments, in terms of the government or policymakers, many of them don't have what the system is. Even though they know how to use AI or how to create a guideline or governance, document for AI or AGIs, in the future. So my question is, to what extent do you think government or policymakers should know or to have a comprehensive understanding of what system is or how system works?
Yes.
So you think
they should definitely? I think that so policy regulation are important in every field where there are concerns about safety or inequality or various other kinds of things that we care about. AI clearly is one of those areas, and it's dismaying to me that so few policymakers actually understand, what they're trying to make rules about. For me, big successes in regulation are easy to point to, like aviation and automotive industry would be good examples, where the rule book got longer as accidents happened and as improvements became possible, and the safety of those systems and their reliability and the number that are, of cars that are lemons and so on, like all these figures of merit just improved and improved and improved. And a lot of that was because of rules, right? Or getting rid of lead in gasoline, getting rid of freon. These are big regulatory wins. Unfortunately, to be honest, I see very, very few moves in AI regulation that look to me, so obviously like they're going to produce those kinds of wins. And I think a part of it is because of a lot of posturing, and a part of it is because a lack of connection between those rules and the deep understanding of the realities of those systems. We probably need to be faster about and more responsive about how such regulation occurs, and maybe try various things as well and see what works best.
Thank
you. It's scary to think that we're just a more evolved neural network. Do you think we should stop the development of AI because we're so similar to it?
And I mean, obviously, I'm getting paid to say no, so yeah. But no, I would say no even if I weren't getting paid to say no. And the reason is that I think we need more intelligence now, not less. I mean, that's the short version. Most of what we talk about when we talk about intelligence is already collective human intelligence anyway. And we often think about AI as being some alien intelligence. That's the way this book that I kind of hate read, over the last days of Eliezer Yudkowsky and co. And Suarez, right? If anybody builds it, everybody dies. Is premised on the idea that AI is an alien and it's weird and foreign. When in fact, like the moment when we got AI to start to actually happen was literally by training it on us, on what we make and are. In that sense, AI is human. If you think about human intelligence as being inherently collective, this is a part of that same complex. So, I tend to think of the human superorganism as including, cows and wheat and people and engines and computers and all of that stuff, and that's a symbiogenesis, right? And if we think a little bit more in those terms and a little bit less in these sort of classically Darwinian terms, I think it's both better for our mental health and more constructive in terms of devising policies. And we have a lot of problems that we've got to solve now, right? From ecological to new sources of energy, to new ways of thinking about how governance can work and how to make agreements with each other. There are many reasons that I think this can be really good if we lean into it.
Hi, I'm a fellow at the Science, Technology and Society program here. You brought a case where you reflected on what is life, what is intelligence, but you didn't mention about what is artificial. Part of your last answer kind of touches on my question. Would you now or in the future draw a boundary of what is artificial intelligence and natural intelligence? And depending on your answer, to what extent do you see hybrid intelligence in the future?
Yeah. Well, in that sense that we're all part of the same big system, it is hybrid. Artificial is, I would say the compute. This is an artificial computer, for instance, right? Whereas natural computers are like our ribosomes and stuff. So we discovered computation rather than inventing it. It's not just an engineering discipline; it's a scientific field. And I guess one way to think about what artificialization is when we discover a natural principle and then we make we plan and make something that uses that principle. We engineer with it. When you start to think about that, you start to ask yourself questions like, well, is fire artificial digestion? Our guts became much shorter once we began cooking with fire. And so we've already engineered ourselves or made a kind of hybrid digestive system that includes kitchens and pots and stuff, as well as stomachs. We used to be covered with fur back, in the earlier part of this plot, and now we're all wearing clothes. Is that artificial fur? I think so, and it's already modified our bodies. So we've been playing this game for a long time, I guess is my point.
I'd like to push a little bit more on the question that was asked by this gentleman about regulation. And you're like, yeah, it'd be great if it was like good regulation. What in your mind would be good regulation on this, since you are an expert on the topic and our policymakers need to learn more from people like you?
So, I mean, this would be the topic for a whole long discussion in its own right. But I'll give one example. I think that system prompts are actually much more important to be public than weights, for instance. Because often when a model has various ideological biases or or intents or whatever, like those are encoded in the system prompt, it's already human understandable and short. So clarity about those would be great. I also think that that we don't. I mean, I may be, somewhat of an expert at AI, but I'm not an expert in what the right rules are going to be, and nobody is. I would say this is similar to the internet in the 1990s. You could be a great internet engineer and have developed, all the packet switching technologies and so on that enabled it, and still have no idea what kinds of rules would work in order to encourage the growth of all the things that were good that came from the internet, but also mitigate some of the problems that come from social media, which I do think could be helped, right, by regulation. But we made all kinds of nonsense rules in the 90s, which had unintended consequences, and didn't either ameliorate the things that they intended to ameliorate, or had or damaged things that were unintended. So even though I'm an AI expert, I don't think that I'm an expert in knowing what those are. I think that we need to try stuff, and we need to be curious and think about this like scientists, and observe when something looks like it's going wrong, and measure and act, and maybe try different variations on rules, perhaps in different places or different domains, and be responsive.
The speed, I think, is the hard part. Just like the internet, the speed, it happens so fast that doing some of those things can be very hard.
I completely agree. That's the biggest challenge.
There's an online question. So we have an online question from Ellie Jackson. If AI is fundamentally a collection of human intelligence, then what rights does AI have? How are you thinking about this, and how do we as a society prepare?
Okay, so I write about this a little bit in the book as well. There are some philosophers who believe that intelligence and or sentience and or theory of mind and or consciousness imply rights. I'm not in that category. I think that it was a big step forward when we as humans decided that we wanted to apply certain moral and ethical principles, universally to other humans. When the sort of all men are created equal was a good advance. An even better advance was the UN Declaration of Human Rights that said, by the way, it's not just men, and so this we've evolved in our thinking about what these rights and responsibilities and moral patience should look like among people. But I think that we sometimes have the illusion that those are God-given, or that there's a truth about what they should be, with a view from nowhere. And I don't think that's the case. I think that there are agreements that we make with each other for our mutual flourishing, and they're not based on some absolute rational thing either. We may have perspectives, that differ about exactly when in a pregnancy, if at all, right, the fetus becomes a person that has those kind of rights. Is it discontinuous? Is it not? We may have disagreements about people with profound disabilities or who have become brain dead. People have legitimate differences of opinions about these kinds of things, and I'm not sure that there's an oracle we could ask to say who is right about that sort of thing. So my view with respect to models is that I've emphasized all the ways that they're very similar in the way they think in a lot of ways to people, but that doesn't mean that all of those same kinds of agreements that we've made with each other apply in any obvious way, or would make sense to apply in those ways. Even if you could, as a hypothetical, right, imagine uploading a person, right? This is very, very hard. We're not anywhere close to being able to do that, but let's pretend for a second, right, that you could run yourself in simulation. Should the simulation have all the same rights, as a person? If you say yes, well, first of all, if you say no because it's just a simulation, then it's a little weird, because I don't think the experience of being in a simulation would be less or different from the experience of being here, you and me. At the same time, there are many deep practical problems that would immediately arise from applying that franchise in the same way, right? You could copy yourself a million times. What if some of those instances, perform some terrible crime, but then you terminate that job, and then well, it's not me, it's not the same one, right? So many things about the arrangements we've made depend on us having bodies and interacting with each other in certain ways that I don't think you can generalize them in any simple way.
Hi. So I don't know if we both are the only sci-fi nerds here. So I won't ask you in front of everyone what happens in your mind when you see Terminator series, but I think I have an idea. You talked about like the next stage and that AI is just another interpretation of us or the next level or the next fur or whatever. But I don't think that's the topic. The topic is how powerful it can be in comparison to us. And that's the thing that people are afraid of. Put Terminator series aside. Okay, so it may be based on us. It may have the same access to the same things that we have, but the power of computation and velocity, that's the difference. And obviously the ability to do stuff afterwards. So that's my question. How do you see that?
Well, so first with respect to sci-fi, you know, the problem with sci-fi, I mean, so on the one hand, sci-fi has been tremendous, you know, generator of ideas and of possible futures. You know, sci-fi writers are the best futurists in a lot of ways. But the problem is they also have to write stories that have plots, you know, and a plot means conflict, and you know, and mortal danger, and you know, somebody having to save the world, and you know, and so on, and you know that. Right. I'm not afraid of that. And you know, I mean, The Matrix, right, is a cool story, but in order to make a conflict between you know, the AI and the people, you have to make a plot device whereby they feed on our cerebrospinal fluid, which is ridiculous, right? So you know, the need to make a plot means that dystopias are favored relative to utopias, or I don't know what you would call something that is not neither a utopia nor a dystopia, but like reality, you know? Yeah. There are writers who do play in that space. Kim Stanley Robinson would be one who I really enjoy. I don't agree with all of his conclusions, but I love his books, and he is doggedly neither utopian nor dystopian. He thinks about the middle space in a way that I think is really cool. Now, you know, am I afraid about AI getting much smarter than us? Question. I mean, which us do we mean? Again, if we define us as, you know, to the exclusion of AI as an individual, then I think it's a very similar question to, are we afraid of cities? Because, you know, cities move so fast and so much more is going on than a person can understand. You know, if you're a medieval villager, I could understand fear of the city easily, right? You don't know all of the people, you know, they have so many specialties and so many things. You can't even imagine most of what they do. You know, I wouldn't be able to, you know, go to all the events or understand anything that is going on. I don't even understand the politics of this place and how it runs. And somehow we're okay with this living in cities, some of us. That is also true. But remember that the city is made out of people too. So, you know, can I imagine futures in which, you know, differentially AI-enabled people are, you know, have very unequal outcomes relative to people who don't, you know, who don't use AI? Yes, I can imagine this. If we don't, you know, work to do certain forms of redistribution or of universal franchises or whatever, and I'm in favor of those kinds of schemes. But I see it less in terms of AI versus human than I see it in terms of inequalities that may rise out of control. And we already are seeing dramatic rises in inequality that, you know, that worry me for all sorts of reasons.
Hi, thank you. Maybe a little bit to what you talked about with like the shortened gut and like getting rid of fur. As a student right now in school, when AI is going so fast, it feels very weird as to, should I even be learning this? Do I even need to know this? So I guess maybe if you are designing education or even a policy school more specifically, what do you think are things that, you know, theoretically AI really can't do, that we really definitely need to know and learn and do by ourselves? And what do you think it's just, us feeling, I don't know, scared that we are not getting rid of in our education system or curriculum or training?
This is a really tricky one, and I don't know the answer. There's this old saying, every augmentation is an amputation. I worry about that. I mean, this is, again, it's an age-old problem. Famously, I'm trying to remember, it's Aristotle who complains about literacy, that it's going to prevent, it's Socrates. But nobody's going to know how to memorize stories anymore, because you can just look it up. There's a whole bunch of things that become weaker in the human mind when you become literate. And that is true. Those things really are the case. These famous stories of illiterate people who have the entire Bible memorized and stuff like it's true. You can memorize things a lot more easily if you're putting pressure on that part of your brain, because you can't just look stuff up. So I worry about de-skilling. And I have my own moments of moral panic, but then I think about the same debates with calculators in classrooms. I think about the fact that I was obsessed with making sure that I knew how to take square roots by hand, and I'm proud that I can, but actually nobody cares, because you're just are we going to feel the same way about things that we consider to be really fundamental today, like being able to write? I don't want that to be the case. I take a lot of pride in my ability to write as well, and I don't want the kids to all grow up not knowing these things. But I don't really know where it's going. I'm selfishly glad that my kids are old enough that they learned how to do all of these things and are able to turn on that jetpack, after having all of these skills, rather than being tempted to do it before they've developed them. But I also don't think it's right for teachers to do the thing that that they attempted with, no calculators allowed. We're not, no, it's actually important to learn how to use and augment also. So I don't know. There may be specific things you have to do some essay writing in class as well, for instance. But then you can turn on these various augmentations in other settings. I don't know, but I would say somewhere between the just anything goes, and you can de-skill yourself in any way you want as long as you get the job done. Somewhere between that and the other extreme of stick your head in the sand and pretend it's not there.
Very good. We are past our time, but this has been a really deep, fascinating look at these deep fundamental questions at the end of, simple questions: what's life? What's intelligence? And what's our relationship with each other and with machines? So thank you very much. It's been fascinating.
Thank you, Ricardo. Thanks all of you.